My name is Leo, and this is my presentation on Lab 3 of circuits. This lab investigated how DC and RC circuits behave by tracking current, voltage, and capacitor discharge. I used the PhET circuit construction kit to build the circuits and Excel to analyze the data. The system included batteries, resistors, capacitor, wires, and ideal meters. Overall, the series circuit carried the same 0.02 amps throughout, while the capacitor voltage decreased exponentially with a time constant of about 5.94 seconds. Three principles guided the analysis lab. First, the node rule states that current entering junction must equal the current leaving it, which explains why the same current flows through a series circuit. Second, the loop rule says that voltage changes around a complete loop adds to zero. And finally, Ohm's law relates voltage drop to current and resistance, so a larger resistor has a larger voltage drop. To test charge conservation in the series circuit, I first calculated the total voltage from the two batteries as 3.0 volts. The two resistors add up to 147 ohms, giving a predicted current of 0.0204 amps. Since charge has only one continuous path to follow, the current must be identical everywhere. Both simulated ammeters read 0.02 amps, which agrees with the prediction and confirms charge conservation directly. Next, I reversed the connection of one ammeter in the same series circuit. Before the reversal, both meters measure 0.02 amps, and afterwards, the current remains 0.02 amps. This is because the simulated ammeter is ideal, meaning it has zero resistance regardless of its orientation. Reversing it does not alter the circuit's total resistance or create another path, so the same current continues through every component. Here I replaced an ammeter in the series path with a voltmeter. The current immediately fell to zero because an ideal voltmeter has extremely high resistance, effectively opening the circuit. With no current flowing, neither resistor has a voltage drop. Since V equals IR, the meter read negative 3 volts because the probes were reversed, but its magnitude matched the full voltage supplied by both batteries. This slide shows how 3 volts supplied by the batteries are distributed around the series circuit. Using the calculated current of 0.0204 amps, the 47 ohm resistor drops to 0.96 volts, while the 100 ohm resistor drops to 2.04 volts. Ideal wires and ammeters have no voltage drop. Together, the two resistors drop exactly, balance the battery voltage, clearly confirming energy conservation through the loop rule in the circuit. To measure voltage without disturbing the circuit, I connected the voltmeter in parallel with the component of interest. The ammeter still read approximately 0.02 amps after adding the voltmeter. This happens because an ideal voltmeter has extremely high resistance, so essentially no current enters its branch. Since the added branch contributes almost no current, the total resistance of the circuit and the series current remains unchanged. And next, I place an ideal ammeter in parallel with the 100 ohm resistor. Because an ideal ammeter has nearly zero resistance, it provided an easier route for charge in the resistor. The 100 ohm resistor was therefore effectively bypassed, leaving approximately 47 ohms of resistance in the main loop. The current increased from 0.02 amps to about 0.06 amps, matching 3 volts divided by 47 ohms as predicted. Finally, I identified which elements contributed resistance to the original series circuit. The two labeled resistors were 47 ohms and 100 ohms, so their series combination was 147 ohms. In the ideal simulation, the wires and ammeter were modeled with zero resistance. Therefore, all the circuit's resistance came from the two resistors, which is why they alone determine the measured current in the setup overall. After examining the steady DC circuit, I moved to an RC circuit to study how capacitors store and release energy. During charging, the battery drives charge onto the capacitor, so its voltage rises towards the battery's voltage, and during discharge, the battery is removed and stored charge flows through the circuit from the capacitor. In my data, capacitor voltage dropped from 9 volts initially to 0.28 volts after 20 seconds. To determine the RC time constant, I analyzed the capacitor's discharge data. The voltage decreased from 9 volts to 0.28 volts over 20 seconds. Because the capacitor's discharge is exponential, I plotted ln of V over V naught against time, which produced a linear relationship. The slope was negative 0.1683, so RC equals the inverse of its magnitude, or 5.94 seconds. The R-squared value of 0.9964 strongly supports the exponential discharge model. There are two main sources of uncertainty in this experiment. First, the stopwatch and the discharge switch were started manually, so the recorded 0-second point may not have matched the exact start of the discharge. That timing offset might explain the non-zero intercept and could expect the calculated RC value. Second, the simulation uses ideal components, while real circuits include internal resistance, leakage, and meter resistance effects. To connect these idealized results to real circuits, I consider two situations. A real ammeter has its small internal resistance, so placing it in series would slightly increase total resistance and lower the measure current. Also, with no resistor, the ideal model gives RC equal to 0, predicting instant charging to infinite initial current. In reality, internal resistance and component limits makes charging occur over time. That's the end of my presentation. Thank you for listening.